equation will be always this. So the mild form is not a, for me, the precise meaning of the equation will be always this form. Meaning part of this is the solution of the heat equation as it is there without perturbation, and another part is the perturbation part. P is well, so this equation without perturbation, and this way I value. If sigma is a constant, but otherwise it's just evaluate the right. The question that people ask about this equation is whenever the pathwise, whenever uniqueness holds for this equation, and we basically talk about two notions of uniqueness, the so-called path uniqueness, which means I can give you high choice, and if you have only two adaptive solutions, but if they are equal, then I say on the soil, and I say the pathway. Another option is uniqueness law. I don't give you right choice, but if you can construct two solutions given by different choices, but such as the law, always the law of any two solutions is the same, then we say the uniqueness in law. So, and this is from the notion of uniqueness, this is but what I so when it falls, okay. Before we say about something about uniqueness, in fact, the function value solution for this equation is based on the dimension 1. Otherwise, there are kind of ways to define the solution, but in usual sense, solution is function value itself, and say only dimension, partial dimension. Uniqueness also is pretty the standard result, which says that the sigma coefficient here is Lipschitz. Then pathwise uniqueness follows easily. There are standard arguments that one can borrow from the theory of theory and get this. The question is what will happen when sigma is non-linear. And so when I ask the question whether this is a question where to keep the linear, for this purpose, I think the example, which is called super-Brownian motion. So what is super-Brownian motion? Super-Brownian motion is a limited model of the particle system. You start with time 0 for the particles, you start with forming until time and it's known that as I'm going to motion, which is a measurable process. It's not private. Here we start from measurable process. Yeah? You get cloud particle divided by no measure. Send n to infinity and say what. And in the limit, you get some process. What do you know about this process? First of all, does exist in the dimension. And the one thing to know that you can characterize the whole of this process by Laplace transform. And this is the important part, so I also will call it right. Yeah.
Total measure is 1.
It's order of n. And then the mass always changes.
But you're dividing by n.
Yeah, but the mass changes. It's not necessarily, it's not always 4 particles. It's here, maybe 6. Yeah, so it's always change. So there are models where you can also preserve number of particles which are closely related, but in this model we say it may change, and then it also may die out. In fact, it dies out really and how to characterize the limiting process? One of the ways to characterize it via the so-called this way. I take my measure which I get in the limit, take it at any time t, and integrate this measure against the test function, non-negative test function. And it turns out that I can characterize this Laplace transform via this equation, where ut slows this. Which means I can always characterize one-dimensional time distribution of the process by certain deterministic non-linear reaction to the equation